Here's your video notes for lesson 7.5, which is probability distribution tables. So a discrete probability distribution table is basically going to list all of the possible values that you can have in your outcomes along with the probabilities. And so it says a subset of z is the integers. So we're talking about counts of numbers here. So these are the discrete values. So we have two fair tetrahedral dice. So these are four-sided dice. They look like little pyramids. And they have the numbers 1, 2, 3, and 4. Let B denote the sum of the two values thrown. So we get the values from 2 to 8. And we want to complete the probability table. So let's organize our thoughts here a little bit. So if we have the numbers 1 through 4 on each die, and we're adding them together, then our sums, 1 plus 1 is 2, 2 plus 1 is 3. Our sums would be this. It helps to get a little visual. You can do it without the visual, but I think you might miss something. So this shows all of our possibilities. You don't have to list them. It doesn't take very long. If you look this way, it shows the different sums that we have. And how many times they occur. Since the dies are the same, there's some symmetry there. There are 16 different possibilities. And so out of 16, how many of them are 2? That would be 1 out of 16. 2 out of 16 are 3s. 3 out of 16 are 4s. 4 out of 16 are 5s. And then we start working our way back down again. And so you can note here that these add up to 16 out of 16. So the total probability are all the events. So it says draw a bar chart to represent the probability distribution of B. So essentially, if you're doing that, your bar chart would just have your sums 2 through 8 here and how many times they would occur. So you can make put 2 through 8 here. So you're going to have your different 1, 2, 3, 4, 5. So you can see a distribution of the different sums, and it's symmetric. That is not as important as being able to use this table. You want to be able to make and use this table, but I wanted to show you that. So when they tell you to make a bar chart, you understand. So here's another example. Show that the function defines a discrete probability distribution. So they're giving you some function, and they're saying we're going from 3 to 7. Construct a table of values. If the probability is equal to the function, represent as a bar chart. So we have t being 3 through 7, and the probability is also known as f of t. You can plug in 3 for t, and you get 1/15. And you plug in 4 for t, you get 2/15, 3/15, etc. So again, this one would be 6 minus 2 over 15. And all of those added together would be 1. Okay, so we don't know what this situation was, but we're basically being told that the probability this happens is each of these values. Okay, so that's the kind of question you might get when it says show that. You're just plugging numbers in. It looks really complicated. It's not very complicated. Okay, so here's where the good stuff happens. So we are going to use these tables to figure out expected values. And if you remember from before, expected values are the number of times you do a trial times the probability. So if you have a 33% chance of winning and you play 1,000 times, okay, you're going to win about 330 times. So that's our concept. This means add up all those probabilities. That's all summation means. So we're really just finding all of the expected values in a table. So let's look at our situation. A handbag contains 7 coins and 3 keys. So we have 7 coins, 3 keys. 2 items are taken out of the bag, one after the other, and not replaced. Find the expected number of keys. So we're using some things that we already know on how to find probability to figure out how many keys will we get if we just did this twice randomly. So the first thing you're going to want to do is make a tree diagram. So I have, it's all in a funky order here, sorry. So I have 7 out of 10 chance of getting a coin and a 3 out of 10 chance of getting a key on the first draw. On the second draw, up top, if I got a coin, I'm down to 6 out of 9 coins and 3 out of 9 keys. So this is just what we did last section. Down below, that's a 7. There's still 7 coins left if you draw a key out, and there's only 2 keys left. So I have all my probability situations by multiplying through the trees. So if I added those up, those would all equal 1. So what does that mean? Well, I'm going to multiply these out first. So when I multiply those out, if I'm going to get 2 coins, my probability is 42 out of 90. If I'm going to get a coin followed by a key, it's 21 out of 90. A key followed by a coin is also 21 out of 90. And then 2 keys is 6 out of 90. So what are my situations when it's asking me for the number of keys? Well, I could either get 0 keys, I could get 1 key, or I could get 2 keys. So I need to make a table that has 0, 1, and 2 and shows those probabilities. So if you haven't written that down yet, go ahead and pause and write those down before I go to the next slide. So this is what the probability distribution table looks like. So across the top, I have my discrete values. I could get 0 keys, 1 key, or 2 keys. The 0 key was just one probability. I get 1 keys either of those 2 ways. So I have 21 out of 90 plus 21 out of 90. So my probability of getting 1 key is 42 out of 90. And then my probability of getting 2 keys is 6 out of 90. So if I want to find the total expected value of keys, which is I made my table, I would take 0 times 42 out of 90. That's going to be 0. Plus 1 times 42 out of 90, which is going to be 42 out of 90. Plus 2 times 6 out of 90, which is 12 90ths. So my total expected number of keys, if I draw twice, is 54 out of 90. And you can change that and reduce it. You get 0.6 or 3/5. So if I draw twice, I would be expected to get 3/5 of a key. Now, this is a silly situation, right? We're not going to draw keys out of things. But if I wanted to make sure, like if I was trying to play something to win, I would need to know, like, okay, that doesn't give me a key. How many times would I have to draw to make sure I have a high enough percentage of key to get? And that's the kind of stuff we're going to be looking at. We're going to look at lottery tickets and figure out expected winnings, and figure out whether it's worth the price, that sort of thing. So again, all we're doing is doing expected values like we did before, only we have a whole table of them. The key is that you make this value be what you're trying to measure. So we will do more problems in class.